Today's lesson is going to be on impacts and linear momentum. Our first formula is going to be our momentum formula, which would be P equals mv, and well, m is your mass and velocity is v is your velocity, sorry, and p is your momentum. And for example, if Patrick is 20 kilograms and is moving at 20 meters per second, then his momentum would be 400 kilograms uh, times meters per second. You are going to also want to remember that momentum is a vector quantity. And you're going to use this formula to find whatever they ask you. So whether it be you manipulate the formula to get P or M or V, and just divide by M to get V and stuff like that. The next concept in this lesson is the change in momentum. And the change of momentum can be seen with these formulas right here, and also this final formula up here. And the first one would be mass times final velocity minus mass times initial velocity would equal the change in momentum. You can also do the mass and the change of velocity, mass times the change of velocity. And then finally, you can also use the net force times the change in time. And this all equals the change in momentum. And this one up here is showing you the one using the net force and the change in momentum, which would also be represented by change in mass times velocity over the change of time. Down here would show us a force, the one that was being shown up here, with the net force times the change in time equals the change in momentum. And that comes in handy when you have a force times time graph, a force versus time graph. And with the area, using this, the net force, this triangle right here represents the net force, and the change of time, and this area right here would change your impulse. Would show your impulse, which this area is basically the same thing as getting this whole area right here. And also, the impulse is the same thing as F net, and the change of time equals impulse, or that right there too. The next, and we see an example right here, and this is asking you for force, and we would use the formula shown right here with the change of mass and the change of velocity, which would be, since it is going from 20 meters per second to 0, since it's stopping, as shown right here, since it's stopping, and since it's going from 10 seconds to 0 seconds, so that would be your change of time right here. And so you just plug in everything into the formula and you would get your braking force, which would be 4,000 newtons. So basically, sometimes it's not gonna tell you that it's not gonna be until a complete stop. So you're gonna have to subtract the two values and get something different right here, and then also subtract these two values and get something different right here. The next lesson would be the law of conservation of linear momentum, as you see right here. And we can flip the page to see our formula that we would use, which would be m1 times v1 initial plus m2 times v2 initial equals m1 times v1 final plus m2 v2 final. And this shows basically that in the collision there would be a similar or a proportional collision. So the forces going across would be proportional to each other, basically. And there's two types of collisions: elastic and inelastic. The elastic collision bounces off of each other, and the inelastic collision sticks together. So, say one object's right here, and it's colliding with this one. If they stick together and keep moving this way or this way, it would be an inelastic. But if they collide and bounce off of each other, going this way and this way, then it would be an elastic collision. To find the final velocity of an inelastic collision, you can use m times the velocity of your first object over the mass of your first object plus the mass of your stationary object. And that would give you the final velocity. And you also have to use your kinetic energy formula to find all of these. Well, any portion that they're asking you, whether it be mass or final velocity, anything like that. With an inelastic, you would use your regular formula, your conservation of linear momentum formula, which was already explained, and basically plug in your values, your first mass, your second mass, your final masses, and stuff like that. Anyways, we see an example. I worked it out for you right here, and the question was, 3 kilogram mass is moving at 10 meters per second when it collides to a 2 kilogram mass moving at 5 meters per second. What is its final velocity? So you would plug it in into the formula, and I manipulated it so that I could separate final velocity. So I plugged it in and I came up with 8 meters per second, and you can pause the video to see how I worked it out. The last concept is the center of mass, and the center of mass is basically just, there's a formula for it shown. Oh, sorry. Center of mass right here. There's a formula shown for it, but I doubt they're going to ask anything concerning the center of mass. But here it is. It's the x-axis length over theta of the first mass over the x-axis, the initial x-axis, divided by theta in the initial mass. And basically what it is the center of mass is the point of the system where all masses are balanced.